Scientists have just discovered the closest intermediate mass black hole to Earth, and it's challenging pretty much everything we know about these cosmic monsters. Hey space fans, Mayukh here, and today we are diving into the groundbreaking discovery that's literally shaking up the world of astrophysics. You might be wondering, what exactly is an intermediate mass black hole, and how close we mean when we are talking about these cosmic distances? And why is this discovery so important? Well, buckle up, because we are about to embark a journey to Omega Centauri, a globular cluster about 16,000 light years away from Earth, where Maximilian and collaborators have found evidence of a black hole that shouldn't quite exist according to our current understanding of the universe. Let's start with the basics. What exactly is an intermediate mass black hole? Imagine you're at a cosmic buffet. On one end, you have stellar mass black holes. These are like the appetizers, weighing in at about 5 to 100 times the mass of our sun. On the other end, you have supermassive black holes. They are the main course. These monsters weigh around millions to billion times the mass of our sun and lurk at the center of pretty much every galaxy we know. But what about the space in between? That's where intermediate mass black holes comes in. They're like this elusive middle course that we astronomers have been searching for decades. These cosmic middleweights are thought to range from about 100 to 100,000 times the mass of our sun. But here's the kicker. Until now, we have had very few confirmed observation of these middleweight black holes. They're like the Bigfoot of the cosmos, often talked about, but rarely seen. But this new discovery in Omega Centauri might be just the smoking gun that we've been looking for ages. Now, with all that out of the way, let's zoom into Omega Centauri. This isn't just any other star cluster. It's the largest and the brightest globular cluster in our Milky Way galaxy. Imagine a cosmic snow globe packed with millions of stars all orbiting around a common center. For years, we astronomers have suspected that there might be something massive lurking at the heart of Omega Centauri, but proving it has been like trying to find a black cat in a coal cellar at midnight. That is, until now. So the million-dollar question: how did astronomers manage to spot this elusive cosmic beast? Well, they used a combination of cutting-edge technology and some good old-fashioned patience. Allow me to break down the process for you. First, they turned to our trusty cosmic eye in the sky, the good old Hubble Space Telescope. But they didn't just make a quick snapshot and call it a day. Oh no, these scientists on the paper are marathon runners of astronomy. They analyzed over 500 Hubble images taken over a whopping 20-year span. That's literally longer than some of you watching have been alive. Now, imagine trying to spot the movement of a snail from an airplane. That sounds impossible, right? Well, that's basically what these astronomers did, but on a cosmic scale. This technique is what we call as astrometry, which is the precise measurements of the position of the movement of stars. So how does this work? Basically, we compare images taken years apart. They're created in what essentially is called a stellar time-lapse video. You take an image when at position A, you wait for 6 months until the sun makes half revolution around the sun, and you take the image of the point in the same way. So you basically take the advantage of an effect called parallax. That's when you look at an object by closing your eyes left and right. That just gives a really precise measurement. So in this time-lapse video, they spotted something really extraordinary happening. 7 stars in the very center of Omega Centauri were moving at breakneck speeds. We are talking about stellar race cars here, folks. These stars were zipping at around 250,000 kilometers per hour. That's wild. Imagine massive stars like our sun whizzing by 100,000 times faster than a bullet. That's even crazy to imagine. But here is where things gets interesting. These stars are moving faster than the escape velocity of the cluster. In other words, they're moving so fast that they should be flung out into space like cosmic spitballs. But the fact that they're not can only mean one thing. They are being held by place by a gravitational pull of something incredibly massive. Something, you guessed right, like an intermediate mass black hole. Now you might be thinking, couldn't this just be a coincidence? I wouldn't blame you if you thought this could be just a coincidence. Maybe these are just random fast stars. Why not? Good thinking, but Maximilian and collaborators thought this way ahead of you. They calculated that the chances of finding this many speedy stars in such a small area by pure coincidence is just like winning a lottery while being struck by lightning twice. That's pretty much impossible to happen. There is only one smoking gun evidence that this has to be an intermediate mass black hole. But they didn't just stop there. They also measured the acceleration of these stars. Imagine trying to measure the change in the speed of bullet while it's still in flight. That is the level of precision we are talking about here. While they couldn't measure the exact accelerations, but the limits they found perfectly fit with what you would expect if the stars were orbiting a black hole. This is pretty common in astronomy. We make real-life models and we try to match that with observations and see if that makes sense. If it does, then yes, your model was successful in explaining something that's actually happening out there. So through this massive astronomical detective work, combining long-term observations, precise measurements, statistical analysis, computer modeling, Maximilian and collaborators have built a compelling case for an intermediate mass black hole hiding in plain sight in our galactic backyard. So we have found an evidence of an intermediate mass black hole. Big deal, right? Well, it is a big deal, and here's why. First, discovery helps us fill in the crucial gap in our understanding of black hole evolution. It's like finding the missing link in the black hole family tree. This intermediate mass black holes could be the seeds from which supermassive black holes actually grow. So far, this link was completely unknown to us and it was all theory and speculation. But having an observational evidence does help. Of course, no one is claiming that for sure it's that. We need more statistics, we need more observations, we need more follow-ups, but this is definitely the step in the right direction. Secondly, it kind of challenges our models of globular cluster formation. Globular clusters are some of the oldest structure in our universe, and finding a black hole in one raises one big question. How did it get there in the first place, and how it's affected the cluster over billions of years? But before leaving, here is the final twist. According to our current theories, the black hole shouldn't exist. It's too massive to be formed from one single star. But again, too small to be a supermassive black hole. Its very existence is forcing us to rethink our models of black hole formation and growth. And there you have it, the closest intermediate mass black hole ever discovered right at our cosmic backyard. If you found this mind-bending, you are going to love the video that I recently made visiting the Very Large Array and explaining how radio telescopes actually work and help us image the cosmos. Do check it out. And for all of those new in this channel, I am Mayukh, I am a PhD candidate and I love making videos on astronomy and space. Consider subscribing if you learned something new. Till then, I'll catch you guys in the next one really soon.